Here we go. All right, so the domain, of all polynomial functions is the set of real numbers. Okay, so our domain of x cubed minus 2x plus 1 will be all real numbers. Now, if you think about, for example, that x squared, a parabola, that's a polynomial function. Now, think about the range or the outputs. Okay, think about a parabola for a moment. That image in your mind. You got a parabola. Are the outputs all real numbers? No, clearly not. If we think about our u, if it opens up, there's a limited minimum number and it doesn't go below that. And if your parabola opens down, there's a maximum that it doesn't go above. So, now that's just for x squared, but in this case, do you guys happen to remember from Algebra 2 that an x cubed looks like this? So in this particular case, the range is all real numbers. And if you think about, do you remember our end behavior last year? Remember end behavior where we said as x goes to infinity stuff? Think about x odd. Wouldn't those always have a range, negative infinity to infinity? It might have wiggles in the middle as you do x cubed and x to the fifth, but essentially it is going to shoot from negative infinity to infinity. All right, how about in letter B? If you have a square root, do you remember we talked about this in our last class? What were the two main functions we had to be worried about for domain? There were two main problems. Tyler?
Is it like square roots and then if x is in the denominator?
Right, exactly. Fractions where x is in the denominator and square roots are even roots. So to do the domain here, since it's underneath a square root, we're going to set x minus 2 greater than or equal to 0. So x is greater than or equal to 2. And then we can convert that into our interval notation. Now, in order to do the range, you want to think for a moment. Okay, it starts at 2. And it's going to the right. X is going to the right. So if I plug in 3, that's 1. And if I plug in, say, 6, that's 2. So here's our square root. Remember, we did our care roots. So now let's think about the range. Look at those output values. What would be the range then for this? What are the possible y values that you see on the graph? John?
Well, the number is greater than 2.
Say that again, I couldn't hear you.
Would it be all the numbers greater than 2?
Greater than 2, but look, y is down here at 0.
All the numbers greater than 0.
Yeah, how about
Greater than or equal to
y is greater than or equal to 0? Do you see that? Yes, I think you were thinking your x's. Now the range are the y values, so it's going to go 0 to infinity. Okay? All right, now in the next example, it says use the vertical line test to determine whether y is a function of x. So what I want you to do is I want you to take a moment, if you need to, make a table, but make a sketch. Make a sketch of the graph of each one of these and determine whether it's a function or not. So in letter A, we know this one looks like this. So yes, it passes the vertical line test. And letter B, it's a good thing that we just reviewed this. This is the general equation for a circle whose center is at the origin. Okay, so you should become more and more familiar with your equations. Like when you see an equation, you should have a picture in your mind as to what the graph looks like. In letter C, you might end up adding 1 to both sides to see that that's a parabola. And we don't need a tremendous amount of detail, but we know it opens up and we know where the lowest point is. So it passes the vertical line test to show it is a function. Okay, does that make sense? Alright, the next example says find the zeros of each function, and then we're going to verify it graphically. Can someone tell us what is a zero? Or what's another word for zero? It's an intercept, and it's actually the x-intercept. Another word you might see is a root or a solution. Okay? Zeros are another way to say the x-intercept, a root, or a solution. So the zeros are when y is 0. So if I set f of x equal to 0 and I have a quadratic, Stephanie, what's usually the first thing we do with a quadratic when we're going to try to solve it? Factor it, exactly. This is an easy one to do by trial and error. To get 2x squared, you put a 2x and an x. To get a 1 at the end, you need a 1 and a 1. Then do your FOIL. The outer is 2x, the inner is 1x, but I need a minus x in the middle. So x is negative 1/2, and x is positive 1. Alright, so here's what we're going to do. It said verify it graphically. So I want you to take out your graphing calculators. And in your y screen, let's do 2x squared minus x minus 1. Okay, again, in your y screen, enter 2x squared minus x minus 1. And maybe we don't know what we were doing last on the calculator, so we'd like to do zoom 6. And what I want to refresh your memory on is using the feature on your calculator that finds x-intercepts or zeros. Does everybody have it? Okay, here's what you're going to do. You're going to press second trace. Second trace. And there, option 2 says 0. Now let's go get the one that's on the left, and so what you have to do is you have to get that little flashing cursor so it's just a little bit to the left of that x-intercept. So I'm going to press enter, and then it's not that I need to get to the right side of my graph, I need to get just a little bit to the right of that x-intercept. Press enter, and on guess, just press enter. And we got negative 1/2, and the calculator says negative 0.5. Now let's repeat and get the 0 that's on the right side. So we go second, trace, select 0, and now I want to see, it's right over here, so I want the flashing cursor a teeny tiny bit to the left of that x-intercept. Not to the left of the entire graph, just a little bit to the left of the x-intercept. And what I really like about my calculators, do you guys see? Yours should do the triangles, but if you have this new TI-84 color, mine's making these dashed lines that's saying the x-intercept is in between those two spots. That's what the triangles mean. And it's telling me x is 1. So, one of the key things you're supposed to be able to do on your graphing calculator is find x-intercepts or zeros. Anybody having any trouble with that? Anybody get an error? If you get an error, you were probably on the same side twice. Okay, letter B. If we want to find the zeros, you get 0 equals the cube root of x minus 1. And one of the things I calculus is that you have so much knowledge that you have to stop and really analyze what do you have and how do you deal with it. So if I have 0 equals the cube root of x minus 1, factoring makes no sense here. So that's, it's like, okay, I'm eliminating that option. I'm trying to solve for x, so I want to undo a cube root. So Josh, what would I want to do to both sides of this equation to undo the cube root?
Cube both sides?
Yeah, exactly. You want to cube both sides. Well, 0 cubed is 0. The cube root and the cube undo each other, so x is 1. And you could verify it graphically. You could look at the graph again. All right, letter C. h of x equals x minus 5 over 2x minus 1. So we're really wondering, when does this fraction equal 0? And you really want to go back to about 3rd grade math when you're dealing with fractions. And you want to think about, how do you know when a fraction equals 0? When does that happen? Stephanie? Okay, so let's write ourselves a note, okay? A fraction equals 0 when the numerator equals 0. Why can't we say it's when the numerator and the denominator equals 0? Why don't we look for both places? Abby, do you know, why don't we set the denominator equal to 0 as well? Well, why don't you have to? Or okay, 0 divided by a number is equal to 0, but what happens when you take a different number divided by 0? You can't do it, it's undefined, right? So it's undefined to have the denominator equal to 0. So we're just going to set x minus 5 equal to 0, and so that's just x equals 5. Let's, and think about this graphically. We'll pop this one in the calculator and look at it. What is actually happening on this graph when the denominator is 0? That's what? X equals 1/2. What's happening graphically? Tyler?
Is it an asymptote?
Yeah, it's actually a vertical asymptote. So let's go back to the calculator. Let's go to our Y screen. Clear it out. Remember, you have to put numerators in a parenthesis and denominators when there's sums or differences. Otherwise, you're going to get a very different looking graph. Okay, so we can see here that there is, in fact, a vertical asymptote at x is 1/2, and there is a 0 at x equals 5. Okay? All right, a function f is even if for each x in the domain of f of negative x equals f of x. A function f is odd if for each x in the domain of f of negative x equals negative f of x. You guys remember in the last section when we replaced x with negative x and we got the original function back? What kind of symmetry was that? When you replace x with negative x and you get the original equation. Y-axis, okay? So this is in fact y-axis symmetry, and I want to make a nice connection here. We're saying that a function is even when it has y-axis symmetry. So if you think about it, if I think about y equals x squared, and it's x to an even power, parabolas, if they're, vertexes on the y-axis, it has y-axis symmetry. So it's sort of easy to remember. Y-axis symmetry are even. Now, the second one with odd, they're saying you replace x with negative x and you get a negative y. What kind of symmetry was that? It's not being stated the exact same way, but it really is the same thing. This is origin symmetry, okay? This one's origin symmetry.